When we finish talking about energy in first semester physics, we then turn to power, where power is defined as the amount of energy used in a given amount of time. We're going to do the same thing now. Now that we've talked about electrical currents, we are ready to talk about electrical power. Now, as I just said, power is defined as the amount of energy used in an amount of time. Now, energy used is probably a misnomer because really energy isn't created or used or destroyed. Conservation of energy. So really we're just transforming energy from one form to another. So we're looking at power as being the amount of energy transformed in a given amount of time. Now, this is what it would look like here. But remember that the potential energy that we have been calculating for electricity, we defined this in chapter 17 as the amount of charge times the voltage. Well, this is what the potential energy would be for one individual charge. We want to know for the total charge, so we're going to use capital Q instead. So the amount of energy that's transformed would be Q times V. And power would then be QV over time. But look at this here. We can separate this to look like Q over T times V. Well, Q over T, what's that the definition of? That is electrical current. And so now we have a new equation for electrical power. Electrical power is the current times the voltage of a circuit. Now, just as before, the unit for power is the watt. Now, before, we said that 1 watt would then equal, so power is equal to energy over time. So 1 watt would equal 1 joule divided by 1 second. But we can now make a second relationship. So power is equal to current times voltage. So 1 watt would then be 1 amp times 1 volt. So there's that relationship with units as well. So that's the unit of power with the watt. But for ohmic devices, that is devices where resistance is involved, we can make the following substitutions using Ohm's law. V equals IR. If we substitute V directly in, then we get current times IR, current times resistance, so power would equal I squared R. This would especially be useful when you are dealing with circuits where you are worried about current load. This is, for example, in your houses. If you have too many appliances in your house, then you're going to be changing the resistance, increasing the current, and by increasing the current through those resistors, you're going to lose power. So this is commonly an equation for power loss. So point being there, if the current is too high, you're going to be releasing a lot of power through the resistance of the circuit. And if you release too much power, it overheats things and can thus start a fire, a house fire, due to overloading a circuit. And we'll talk more about that in the next couple slides. Another substitution, if we solve for current would be voltage divided by resistance. If you take that and you substitute that in for the current, then you end up with another form where power is equal to voltage squared divided by R. Again, we can talk about power loss here, but based on voltage instead of resistance. Now, when you get a power bill, really power bill is a misnomer. The reason why is when you pay your power bill, you're not really paying for power, how quickly you use energy, but you're paying for the energy itself. And so since power is equal to energy over time, then energy is going to equal power times time. So the energy is going to be the power consumption multiplied by the time. And if we use the units of kilowatts and hours, kilowatts for power, hours for time, then that gives us the unit kilowatt hour. So 1 kilowatt hour would be, well, 1 kilowatt, which is 1,000 watts, times 1 hour, which is 3,600 seconds. And remember, a watt is a joule per second, so the seconds cancel here. So you end up with 3.6 times 10 to the 6th joules. 1 kilowatt hour of energy is equal to 3.6 million joules. Just as a comparison there for a relationship. Now, when you wire a home, obviously you're going to measure the energy used in kilowatt hours, which means you're going to pay the bill by how much energy you use, not the power consumption, by the energy. But also in a home, your circuits are built in a way that wires have low resistance. This is good because the lower the resistance, the less heat is pulled out, and so it's safer to have low resistance wires. However, because of this equation here, if the current is high enough, then the power will increase and wires can become hot enough to start a fire. This is a huge worry and has been for quite a while. So we have a couple of devices that help us to disconnect when the current goes above some predetermined value. The first device is called a fuse. Now, if you have a circuit, then you have this fuse box here, and the fuse can look like any one of these. In your car, you'll be using devices like these. In small appliances, you'd be using fuses like these, but in your house, you'd be using a fuse that looks like this. They're all different types of fuses, but the principle is the same. If the current gets too high, thus producing a lot of heat, putting you at risk of starting a fire, this fuse breaks and disappears. When it breaks and disappears, that disconnects the circuit and the current stops. All the lights and appliances all turn off. And you have to go in, pull out that burned fuse, and pull out a brand new fuse and replace it to get it to work again after you fix the circuit so its current isn't too high. Now there's another invention which makes it a lot easier, and that is the circuit breaker. They are much more common because they are easier to deal with. You don't have to keep buying new fuses and throwing away the old ones. It's just a lot nicer. What you have is your electric circuit here connected this way, so you have a complete circuit. But part of that circuit is this metal rod, which is connected to a spring, and and you have this bimetallic strip, which will heat up if the current is too high. And if it heats up to a certain point, it's going to start to bend. And if it bends to a certain point, the spring will push the rod down, thus disconnecting the circuit. And disrupting the circuit, it prevents things from getting too hot, and thus you save your house from catching on fire. Now, the advantage to circuit breakers over fuses is that after you fix the circuit, all you have to do is flip the switch, close the contact again, and then you can run electricity all over. And this can happen countless times without having to throw a single fuse away. So that's a very useful tool in a home to prevent house fires.